Well, in this video, we're going to deal with an entirely new topic from exponents. We're going to be looking at complex numbers. And we'll learn what a complex number is and a little bit about how they came to be. And really, when you look at this subject, it goes way back to antiquity, where a lot of math problems originate, with Heron of Alexandria. Now, Alexandria is in Egypt. It was one of the major cultural and learning centers of the ancient world. You probably have heard of the Library of Alexandria, where all of the knowledge compiled to that time was stored in that library. The Romans burned it, and it was a great loss because all of the discoveries of the ancient Greeks went up in smoke. Well, not all of it, but a good portion of it. We'll never know to what extent they understood the world. But Heron, living in Alexandria, living in Egypt, was confronted by the problem of trying to find the volume of a frustum of a pyramid. And a frustum, well, is like a pyramid whose top has been cut off like that. I just threw his... So that's basically what he was trying to find. And it wasn't an easy problem because they had a difficulty. They were able to measure all the angle sides and the base and the top. They could measure directly using tapes or, measuring rods or whatever it was that they used. But they couldn't find the height, h. They couldn't measure it directly. So Heron developed a formula that was to estimate the height of a pyramid without direct measurement. You could use the measurements of the sides and bases and such so that you could find the height. And when he did, let's say this is an arbitrary pyramid. It's a small one. We're not given any units. We have 15 squared. It looks a little bit like our quadratic formula. Remember, where we have ax squared plus bx plus c equals 0, where x equals minus b on 2a plus or minus 1 on 2a square root of b squared minus 4ac. Looks very similar to this. And in fact, I believe they are probably equivalent if I went and carried the math out. So, this is what Heron derived. And using these numbers, if we had a pyramid of this sort, 28 minus 4 on 2 squared. And that yields, well, now let's see, 15 16, that's 12, 225. 225 minus, this is 28 minus 4 on 2, that's 24 on 2, that's 12. So 12 squared times, let's see, 12 squared times 2. Okay, so that's minus 2 times 12 squared, which is 144. So here we have the 144 times 2, that's 88, 288, minus 255, and that's 3. That's 3. That's equal to the square root of minus 33. Now, that befuddled Heron. He knew he had a problem here, because that negative sign, there is no number. There is no number n where there's no n where n times n equals -1. There's just no situation where that's known. And so this really created a problem for Heron, and he ignored that negative sign and just said h equals square root of 33. Well, that was problematic, because Heron could have discovered complex and imaginary numbers 1400 years before they actually were discovered. And so he lost out on an opportunity of going down in history as the discoverer of imaginary numbers. But I wanted to give you a little history on it, because mathematicians were running into these problems, that seemed out of the, they were real world problems, but they were out of the ability of the mathematics at the time to solve directly. And it wasn't until the 14th century when mathematicians from Italy, and what's interesting, in Italy, they were the leaders of math in the 1400s. They had professional mathematicians, and problems would be posed and money paid if these problems could be solved. And so mathematicians set up business solving problems. And there were, let's see, who I had listed a number of them. Mathematicians like Luca Pacioli. I can't say, I'm not Italian, so I'm not going to pronounce these correctly. Scipione del Ferro, Girolamo Cardano, he was very famous. And these mathematicians competed. Nicola Fontana, these mathematicians competed in solving problems. And people would pose problems such as this: x squared plus 1 equals 0. Now, what do you do with something like this? Well, x squared equals -1. And then you have x equals plus or minus the square root of minus 1. Well, again, these problems arose all the time where there was no number where it's multiplied by itself gave the result of -1. So somebody, somehow, somewhere, decided that we can't ignore this situation. We have to resolve it somehow. And so what they did was they created a placeholder, and they called it I for imaginary. And I was the square root of -1 by definition. And that was to solve these types of problems. So in case of Heron's problem, we would have h equals the square root of -33 would equal square root of 33i. And I would be equal to the square root of -1. So here, this is how they got around these difficult problems. And they were arising all the time as people were deriving newer and more complex math problems to solve. So this I has become a very important I equals the square root of -1 has become very important in mathematics. One of the most important entities that has been conceived in mathematics. So much of mathematics would be impossible to solve without this I. In ordinary differential equations, where we have y double prime plus b ay double prime plus by plus c y minus b or d equals 0. And the solution to that is y is equal to plus or minus ix something like that, something to that nature. And when you plug it in, you can solve for the different constants. But without this imaginary number, you wouldn't be able to solve an ordinary differential equation. And I mean, we're jumping ahead, but it gives you an idea of how important this is, because all linear differential equations, ordinary linear differential equations, require they're dependent on e to the ix type solution. And it shows up in so many other areas. So why don't we take a look at this? I has some interesting characteristics. So let's say we make a table, and we have x and we have I to the x. So x is 0, 1, 2, 3, 4, 5, 6, 7, all the way down to infinity, really. I to the 0 is 1, and I to the 1 is equal to the square root of -1. I squared is equal to square root of -1 minus, or times minus the square root of -1 equals the square root, or equals -1. I to the third equals I squared times I, which equals negative square root of -1. I to the fourth is equal to I squared times I squared, which is equal to -1 times -1 equals 1. So we go through this cycle of 1, square root of -1, net -1, and so on. So the pattern is 1, I, -1, -I, 1. And it repeats all over again. I, -1, -I, and we'll make it 8, 1, because I to the 8 equals I to the fourth times I to the fourth. I to the fourth is 1 times 1 equals 1. So this is important for us. We have to make sure that we're careful about the power to which we carry I, because it carries a different value for different powers, and we have to make sure that we're not writing down the wrong thing when we write the answer. So here we got 1, I, -1, I, 1, I, -1, I, 1, and it goes on, cycles forever like that. So we have our table by powers for the imaginary number. Now, imaginary numbers are really hard for us to conceive. It's something that it's not a number system that we can think of. It's really kind of a placeholder in a sense, but they can be used in many different ways. And in particular, they are used in forming complex numbers. Complex numbers. And we're not talking about them complex in the sense that they're difficult, that they're not really difficult. They're complex in that they are made of composites of real and imaginary numbers. So that's why they're called complex, because they're numbers, but they have components to them, components that are real and components that are imaginary. And for example, we have a complex number, we'll call it n, and it's made of a real component and an imaginary component. And that imaginary component can be multiplied by a real component. So, for example, if A is equal to 2 and B is equal to 3, N would be 2 plus 3i. And that's a complex number. It's not really hard. It's not complex in that sense. But when we deal with them in situations that we would deal with ordinary numbers, real numbers, adding, subtracting, and so on, they take on a different they're not as it's not that it's not straightforward, but it's not as let's say you can't be as unthinking about as real numbers like 2 plus 3 equals 5. Well, if you have a complex number n plus p, what do you have? Well, how do you do that? So there are rules for adding and subtracting and multiplying complex numbers. So we're going to take a look at these rules. 1, add. So if we have complex numbers a plus bi added to c plus di, we add the real components and we add the imaginary components. So here we have a plus c plus b plus di, and that's adding complex numbers. Let's say, you see, we can think of other addition problems, like what if we have a plus bi plus c minus di? Well, we add the real components plus the imaginary components. Well, what if we subtract? You can see how we would have many different types of scenarios. So we have to be careful about how we work with them. For example, what if we had a subtraction of a plus bi minus d plus ci? So we have a minus d minus b, or plus, we could say, hey, you see, this is where we got to be careful. Let's be careful about this. Here we have we have a minus d, and we have to add that, and we have b minus c. And what do we have here? We have a plus d plus b minus c. You see what I mean by we have to be careful? We have to make sure that we're consistent with the signs. If we're going to change this, then we have to reverse the order like that. So we just have to be careful of what we're doing. That's a key thing in addition and subtraction of imaginary numbers. Now we have multiplication and division. So let's take a look at multiplication. We have A plus BI times C plus DI. Now, here we must multiply every component. We don't just multiply the real and the imaginary. So here we have to go A times C plus A times DI plus B times CI plus B times DI squared. So now we can take the real components and the imaginary components. Now, I squared is minus 1. So we have AC minus BD plus AD plus BCI. And that's what we have for our multiplying of imaginary numbers. So what if we had something like this? A plus BI squared. Well, then we have A plus BI times A plus BI, and that's A squared plus 2ABI plus B squared I squared, and that's equal to A squared minus B squared plus 2ABI. Okay, and there's one special multiplication that always yields a real number, and that's when you multiply conjugates. A plus BI times A minus BI. We call that a conjugate of this. So A squared minus ABI plus ABI. Those cancel out. Times plus B times negative B I squared. So that's equal to, these cancel out, A squared plus negative B squared times negative 1. So it's A squared plus B squared. And that's a real number. And that can be useful to us, especially when it comes to division. So let's take a look at division. we have A plus BI divided by C plus DI. Well, we can simplify this by plus BI and multiplying numerator and denominator by the conjugate of the denominator. So we have C plus DI times C minus DI times C minus DI. And that's equal to AC minus ADI plus BCI minus BDI squared. And that's over C squared plus D squared. And then that's equal to AC plus BD plus BC minus ADI over C squared plus D squared. And remember, this is a number. These are all numbers. So let us take a look at a real number problem. Let's say we have 3 minus 2i divided by 5 minus I. Well, that would be equal to 3 minus 2i times divided by 5 minus I times 5 plus I over 5 plus I, and that's equal to 15. Let's see, 15 plus 3I minus 10I minus 2I squared. And that's all over 5 squared plus 1. So that's equal to, this is minus 1, so that's 17 minus 7i over 26. And that's equal to 1726 minus 726i. So that would be a division. Now there's another thing that people have done, because complex numbers are made of components, they're composite numbers. You can, like any number system, you can plot them. And you can plot them on a real axis and an imaginary axis. So let's call this the real axis. We'll call that A, and we'll call this B I. And so if we had a number, A plus BI, we can plot them on this, the real part and the imaginary part on this axis system, just like a Cartesian coordinate system. Okay, I made a minor modification. I just called this I. Now let's say we have an imaginary number z, and that's usually how they're represented using the symbol z. Well, we have, let's say, A is right there, and the imaginary part we have B, and we can plot on this scale up to here, and let's say over, it's not exactly square, is it? And we got our spot right there, and that's A, B on this scale. But remember, we can find the components. We got R right there, not a very nice R. R. We've got an angle, theta, and we know that x is equal to R cosine theta, and y equals R sine theta. Well, in this situation, we have x is equal to, let's see, R. R would be the Pythagorean theorem, a squared plus b squared equals r squared. So r equals a squared plus b squared. So we have a, which is a squared plus b squared cosine theta plus b, which would be a squared plus b squared sine theta I. And R is called the modulus. Okay, so we had said that R is the modulus, and that R is equal to a squared plus b squared. But we also recognize that R, the modulus, is also the R equals the conjugates multiplied by each other. So we have a squared minus abi plus abi minus b squared I squared, and that's equal to a, that's r squared, a squared minus or plus b squared, and r equals the square root of a squared plus b squared. It's like the Pythagorean theorem. So that is important for us to look at. Another thing here that's important for us, because we have this in trigonometric form, we need to find theta. Theta in this context is the argument of the trigonometric function. Of the cosine function or the sine function. We didn't cover that in the trigonometric series. I never mentioned that was, I don't believe, that the angle is the argument of the trigonometric function. So you'll hear that term. So how do we find theta? Well, we find theta by looking at this and saying, what is the definition of the tangent of theta? Well, it's the sine of theta over the cosine of theta. Well, in that case, that happens to be B on A. So tangent theta is equal to B on A. But we want theta. So what do we have? We take the arctan on each side. So we have theta equals the arctan of B on A. So we can compress this whole thing into one formula. A plus BI equals, well, we can factor out the modulus, A plus A squared plus B squared times the cosine of, well, let's make this a square bracket, cosine of the tangent, arctangent of B on A, remember that's theta, plus I sine of the arctan of B on A, and there we have it. And that's beautiful. And this is used all the time. This relationship is critical to electrical engineers. So that's a wonderful thing. So let's take a look at a problem now. Let's say we have Z. Z is usually the way we represent or complex numbers, A plus BI. So what if we have Z equals 5 plus 5I? And we're given A, find A and B. B, find the modulus. And C, find the argument. Okay, so we got these three things. Well, since Z equals A plus BI, we have 5 plus 5I, A equals 5 and B equals 5. So we answered the first one, the first question. Second question is, find the modulus, R. So we know that R is the square root of the multiplication of the conjugates. So we have 5 plus 5i times 5 minus 5i to the 1/2 power. And that would be equal to 25 plus 25i minus 25i minus 25i squared, all under the square root. Well, we know these two cancel, and that becomes plus 25 because I squared equals -1. So we have the square root of 50. Well, 7 times 7 equals 49. So it's going to be close to 7. And in fact, it's something like 7.07, I don't know, 11, something like that. It's an approximation. So this is pretty cool stuff. And now we have one more problem. Find the argument. Now the argument, remember, our formula, a 5 plus 5i equals the square root of 50 times the cosine of theta plus I sine of theta. So what we want now is, what is theta? Well, we go to our definition where theta is equal to the arctan of B on A. And in this case, B and A are the same, so we have arctan of 1. And remember in our trigonometry that when we we have a situation where we have x is 1 and y is 1, x equals 1, y equals 1, r equals the square root of 2. This angle, theta, is splits. This is pi on 2, this is 0, exactly splits this quadrant, and so that theta is pi on 4. So that is pi on 4. So that's our argument. So now we've answered all 3 questions. I think we can do another problem. I don't know if it's beneficial or not. And at this point, I think we're just going to consider imaginary numbers. We're not going to do vectors. They're similar in some respects in how you add, subtract, and so on. But we're not gonna do those just at this point. Okay, we're gonna do one last problem here, and there's more we could do, but it requires us to understand calculus, and so we're not going to move that far forward because you haven't any clues to what calculus is at this point. But we're given here an imaginary number, z equals 12 plus 36i, and we're told to find the modulus and the argument. So Remember, the modulus is the square root of the conjugates multiplied by each other. So R is equal to 12 plus 36I times 12 minus 36I to the 1/2 power. So that's equal to 144 minus 12 times 36I plus 12 times 36I. Those cancel. Minus 36 squared I squared, all raised to the 1/2 power. These two cancel out, and we have 144 plus 36 squared. So what's 36 squared? 36 squared, that's 36. That's 1821, 18, 9, 10. That's 6, 9, 2, 1, 1296. 1296 to the 1/2. So we got 144. That's 10, 11. That's 14, 4, 1. So that's equal to 1440 to the 1/2. Well, that's equal to 12 squared times 10 to the 1/2. So we have equals 12 to the square root of 10. And that's what R is. And I don't know if we can simplify that anymore. 10 is 2, 5. Nope, can't make it simpler. So that's our answer there. So we have our modulus is 12 times the square root of 10. The argument. Now the argument here again is the arctan of B over A. So we have theta equals the arctan of B, that's 36 over 12. So that would be arctan of 3. And arctan of 3. So that we'd have to take a look at the trigonometric quadrants here. So when we go back to our roots of trigonometric functions, we know that when we have 1 over 1, the angle is pi on 4 or 45 degrees. If we have a triangle where the base is 1 and the height is 3, so we have 1 and 3. 3 on 1 is the tangent of theta. So we see we're not quite at 90, that's 90 degrees, or pi on 2, but we're much steeper than 45 degrees. And it turns out at this tangent of 3, theta, is equal to, well, let's take a look. I can get a more precise. 71.56 degrees. So it's not quite 90. Oops, that's a decimal point. It's not 90, but it's not 45 either. It's in between. So that's our angle. So our argument is 71.56 degrees. So there we go. We have solved two problems in complex numbers. And I think the next video, it would be better for us to deal with vectors as a separate topic. So there are other problems. There are identities like Euler's identity that makes big use of imaginary numbers. I can't pronounce it, de Moivre. I think it's a French name. He was a French mathematician. He found another identity in complex numbers. But it requires us to understand a little bit about calculus, and we, at this point, can't utilize those tools because we haven't learned anything about the fundamentals of calculus, so we can't derive those. So we'll look at those formulas later. But we took a pretty good look at imaginary numbers and what they mean and how they're computed. So I think this has been a pretty good lesson. I hope you do too. And we'll stop here. And I think the next video will pick up on vectors.